Okay, so thank you guys for attending this RISE tutorial session. And in today's session, we're having Francisco, which will give us a tutorial on torchmil, which is PyTorch library on multi-instance training for histopathology. And I will be letting him describe himself and giving you like the full tutorial now. So please, Francisco.
Yeah, thank you so much for the introduction. I'm very happy to be talking here of this topic. I would like to thank Miguel and Rashid for inviting me to giving this talk. Yeah, let me present my slides and then I will be, I think everyone can see it. Yeah, okay. So first, my name is Fran. Actually, it's Francisco Miguel Castro-Macías, but for short, it's Fran Castro. I'm a PhD student in Spain. Most of my PhD has been about medical imaging, doing things with medical imaging. Especially, I've been interested in this multiple instance learning problem, which is the one I'm going to be talking about here. Yeah, so like in the end of my PhD, we developed this tool, which is called torchmil. And that's going to be like the main topic of today, how to apply this thing to histopathology. Okay, so okay, so maybe if I do like this, you can see it. Yeah, this is the outline or like the structure I'm going to follow today. This tutorial is going to be divided into two parts. The first one is going to be a somehow more theoretical session or like part where I'm going to present the multiple instance learning, and then in the second part I will present a notebook, a Jupyter notebook, where I will show you how to essentially train a multiple instance learning model on histopathology slides. Okay, and for that we will use the torchmil library. So in the first part, these are the first three sections of the first part. I'm going to motivate a little bit the problem, and then I will present formally multiple instance learning, and then I will briefly talk about the library. Okay. I think I cannot annotate and okay. Okay, I need to remove all of, okay, I think I won't annotate because, okay. So in the motivation of this, for the motivation, I would like to talk about how we can do machine learning for histopathology. This tutorial, or this multiple instance learning thing is going to be framed into the computational pathology area, which is the intersection of computer science and pathology. When we talk about, in this tutorial, we're going to be working with this object here, which is called a whole slide image. A whole slide image is obtained when a biopsy is digitalized. Biopsy is the test that pathologists use to diagnose cancer, study how the cells in the patients work, or to even discover biomarkers for different type of cancers. The idea is to extract a piece of tissue from a patient and then analyze it using a microscope. When this tissue is put in a glass slide and digitalized, you obtain a whole slide image, which is the thing we're going to be working with today. So what is going to be our goal for today? It's going to be able to train a model that is able to detect the presence and the location of tumor tissue in a whole slide image. Okay, we would like to feed a whole slide image into the model, and the model ideally would give us something like what is shown in this slide. The model will tell us where the tumorous tissue is. Okay. The problem is working with whole slide images, as you're going to see today, is not easy at all, and I would like to explain why. When When we work with whole slide images, we have to have clear that these images are very big, very large. They are gigapixel size images, which means they cannot be processed at once by a computer, not even, and of course, not by a GPU. So how do we work with them? We need to divide these images into something called patches, okay, which is shown here on the right. For this, we need to separate what is the tissue from the background in the whole slide image, and that is usually called segmentation. This process, the good thing about this is that this process has been standardized by a tool called Trident that was launched last year. So essentially, we just have to feed the whole slide images to this Trident tool, and it will give us the patches. I will show you how you can use Trident in the second part in the notebook. torchmil, the library I'm going to talk about today, is designed to work with this Trident tool. Okay. So let me review some maybe naive idea, but it was actually the first idea that was explored when working with whole slide images. Imagine you want to train a classifier of whole slide images. An idea would be to ask a pathologist to label the patches in a whole slide image. Okay. Something I haven't said. At the end of this first part, there will be a time for questions. So maybe it's better if I answer the question at the end of the first part. Okay. But you can leave them in the chat, and we will answer them at the end of the presentation. Okay. Before starting with the Jupyter notebook. So as I was saying, one idea would be to ask a pathologist to label all the patches in a whole slide image, and then train a model using these patches. You have in the right these labeled these patches that has been labeled. Okay. The problem with this is that this labeling process, labeling patches, all the patches in many whole slide images, is something that is extremely time consuming. There are other problems with this approach that I have listed here, but the most important problem is the first one. This is because first, labeling each piece of the whole slide image is very hard for pathologists. And second, pathologists have other things to do instead of like labeling many patches, which is, as I said, very exhaustive task. So we need to come up with a better with a solution for this, with a better approach. Okay, and multiple instance learning is maybe a solution for this because it allows us to learn without all these labels. I'm going to briefly explain why. Before explaining multiple instance learning in a formal way, I would first like to make an observation about how whole slide images, about the nature of whole slide images in the context of cancer diagnosis, cancer prediction. Okay, so as we said, a whole slide image can be seen as a set of patches. Okay, and these patches can be labeled as I explained before. But we're going to assume that the labels of the patches are not available because in a real scenario, we won't have them. We won't have the pathologists to label these patches for us. Okay, but instead we have something that is very valuable, which is a global label for the whole slide image. If the whole slide image has no signs of tumorous tissue, this whole slide image will be healthy. Okay, but if at least one patch is cancerous, then we can label the whole slide image as being cancerous. In this case, the whole slide image will be cancerous because, as you can see, there are red patches, which means there is cancerous tissue in there. Okay. And the good thing is that this global label is very easy to obtain from the medical records. Patients that have already been diagnosed, the diagnosis is saved in the system, so we can take them and use them as global labels. Okay. The question is how do we learn using only the global label? And I would like to remind you that our goal is still not only to say, okay, there is cancer in the, or there is a cancerous tissue or tumorous tissue in the holocyte image, but we want to find where this tissue is, okay, without being labeled, without the labels that tell us where the tissue is, okay. I'm going to introduce somewhat formally multiple instance learning, but essentially it's what I just explained. In multiple instance learning, we have our data are pairs of bags in the bag label. Okay, a bag is a set, a group of instances, and each instance is some object. We can represent it like as a d-dimensional object. Okay, for us, the instances will be the patches, and the bag will be the holocyte image. Okay, so a holocyte image is a bag, and an instance is a patch. As we said, we have instance labels, but they won't be available at training time. Okay. Instead, we have a powerful relationship between both kind of labels. Okay. As I explained before, the bag label will be positive, will be 1 if at least one instance is positive. Okay, is 1. For example, in this example here, this red box here, can maybe write this red box here is red. Why? Because there is at least one positive instance. And what we observe at training time is this. We don't observe the instance labels. We observe the bag label. And from this, we would like to train a model that is able to localize where the positive instances are. Okay. The same way, the bag label will be negative or 0 if there are no positive instances. There are no positive instances, as I said. In the case of cancer prediction or tumor prediction, it will mean that a holocyte image has no cancerous patches. Okay. Okay, so as I said before, at test time, what we want to do is to have a model that allows us to predict the bag label, which is the color of the square, this here, and the instance label, which are the color of the little pieces inside these images. Okay, these tasks has a name, which are called classification and localization tasks, but it's not very important. So examples of this this framework or setting that I have just explained are, of course, histopathology, but there are many more. For example, when we want to detect intracranial hemorrhages from CT scans, we observe the same problem or the same setting. A CT scan has hemorrhage somewhere if there is at least one slice that shows evidences of hemorrhage. Okay. And there are many more, especially in medical imaging, or not only medical imaging, but in the medical field. Let's say there are many applications of this phenomenon. Okay. But as I said, we're going to be interested in histopathology. Yeah, I would like to briefly introduce a model, which is a little bit, let's say, old. It was proposed in 2018, but it set somehow the framework for what today's multiple instance learning models are doing. Okay, the idea is somehow simple, but is very powerful. This model has one thing that is called the attention pooling mechanism that gives or assigns a value, a number to each instance. Okay. These numbers are called here, the Fs are called attention values. And the attention values are used to aggregate all the representations from the instances into a bag representation. Okay. And then this bag representation here, the set, is used to classify the holocyte image. Okay, how is this defined? The idea is to first convert or transform your input instance using a neural network We'll later talk about how important is the choice of this neural network, because it will be very important. And then we have the attention pooling. The first equation here, the equation that defines the X, you can use any network that transforms a vector into a one-dimensional value. Okay, this is a two-layer perceptron, but you can use whatever you want. The next step is to normalize those attention values using the softmax. And then we're going to use these attention scores, which are the attention values that have been normalized, to compute the bug representation. Okay, then we will just fed the bug representation to the classifier. Okay, why this model is important, or why I say it's important? Because the attention values, as we see here, the attention scores, somehow represent how important is an instance inside the bag. If the attention score of an instance is very large, it will mean that the instance is very important in the bag. Okay. And it has been observed that these attention values can be used to identify which instances are positive. In our case, this means identifying which patches carry the cancerous tissue. Okay. This is an example of a whole slide image. And then we have the patches that have been labeled by a pathologist. And then we have what are the prediction of an ABB model trained. And I would like to note this. This model has been trained using only bag level labels. The model has not been shown any patch level label, and is still able to localize where the tumorous tissue or the cancerous tissue is. Okay, that's why it's important. So the goal of the tutorial of the second part of the Jupyter notebook will be to reproduce this from the start, preprocessing the data, creating the data set, training the model, and visualizing the prediction. Okay, this will be the goal, and it will be very easy thanks to first Trident, because it will allow us to preprocess the size, and second, thanks to torchmil, which will streamline all the model definition, patch, whole slide image visualization, attention values predictions, etc. Okay. So to end this first part, I would like to briefly introduce torchmil, but we were going to be talking about this in the second part. So yeah. Torchmil, as I said, is a PyTorch library for doing multiple instance learning. The idea of this library is to provide a flexible and somehow adaptive framework to build, train, and evaluate multiple instance learning models. For this, we have different modules inside the library. We have a neural networks module that contains different building blocks like transformers, graph neural networks, attention mechanisms, attention pooling, that are commonly used when defining or when instantiating multiple instance learning models. Then we have a hub of models. These are models that have been proposed in the literature, and we have them in torchmil. We don't have them all, but we have a nice amount of models. I think today we have like 16 or something like that, or I don't remember exactly the name. Then we have a data part, which collects some tools, some mechanisms to work with multiple instance learning data. And then we have a hub of popular data sets that are ready to use. Like these are data sets that are usually used in papers to evaluate multiple instance learning models. Okay. And I just wanted to show you some. I would like to show what things can you do with torchmil. These are all models that are available in torchmil, and essentially you can train them and you can obtain predictions with them. Okay. So yeah, I think this is the first part. I would like to stop here to answer any questions. If there are some questions, I think they're in the chat. If someone wants to say something or ask.
Yes, there is one question for you, Francisco, there in the chat,
Okay,
in the Q&A. Can you see?
I cannot.
They say, can this be used for
Yeah.
general medical segmentation task?
Okay, so the question. Okay, let me read it. Okay, I see it now. I think I can read it. Can this be used for? The question is from Roa. I think I spelled it right. Can this be used for general medical segmentation tasks, not only anomaly segmentation, like segmenting some neurostructure from cranial ultrasound, for example, where labels are scarce? In principle, yes. You don't need to always identify an anomaly. The only thing you need for this to work is to have these kind of two-level structures where you have a back label and then you have some fine-grained labels that you don't know, but you know they are there and you want to predict them. So I think it's maybe the thing you are commenting is can be used for that. I'm not an expert in neural structures, but I assume if you have these two-level structure you can use it. Yeah. Okay. Okay.
Okay, there is another question of Abu Bar Shafiq that say that does MIL works for multi-class classification?
Yes, that's a great question. Actually, we are extending torchmil to account for this. Yeah, let me go to the multiple instance limit definition. Yeah, essentially what you're seeing here can be pretty much extended to multi-class scenario. But yeah, it can be extended and there are papers on it. Yeah. And it's actually very useful because actually, when you are working with cancer diagnosis, you don't always have a yes or no answer. You usually have some kind of grading mechanism where the cancerous structures manifestate in different ways. So yes, the short answer is yes.
So the short answer is yes. Right?
Yes.
It supports multi-class classification.
Yeah.
Okay. The next question is from Samuel that say, are the whole slide image have to be converted to tiles or patches before training the model?
Yes. Let me go to this slide. Yeah, so this is the process. As you can see here, you will be given a whole slide image, and that whole slide image has to be segmented and then converted into patches or tiles, as you said. This is a process that has to be done before training the model. Yeah.
Okay, and then there is another question from Venkatesh that say, how is attention score proportional to instance importance?
Yeah, this is, the argument for this is, there is no, I've been thinking about this for a long time, but there is no theoretical answer for this. It's just something that has been observed empirically. When people started to train this model, this kind of models, they observed that when they plot the attention values, they show a high correlation with the instance label. But as I said, this is an empirical observation, and I haven't been able to find a theoretical answer for this yet.
Okay, so empirically, yes. Nice.
Yes.
There is another question in the chat, but not in the Q&A, from Arvin Kumar that say, what about few shot scenarios in pathology?
Few shot scenarios. Okay. I am not aware of any work for this. And I'm not an expert on few shot learning, but I assume there are papers about it. It's just that I am not an expert. Yeah, I think there are papers that work on it, but I haven't personally worked on this topic. So yeah.
Okay.
Sorry.
Okay, here there is another question from Philip that say, how resilient is the MIL library for whole slide images that may have noise within their structure or have other perturbation due to poor data capture during staining, digitizing? How accurate is the classification with this noisy artifacts?
Yeah. Okay. The thing. Okay. So maybe let me try to frame this. When a whole slide image is taken, as Philip says, there can be some noising mechanisms that can affect the quality of the image. And how well will a whole slide, how well will a model classify or detect the cancerous tissue will depend on two things. The first one is this thing, this neural net here. I will talk about it in the Jupyter notebook. And then this is very important, the neural network that you use here. Essentially, we're going to be using networks that have been trained using self-supervised learning. So the robustness of the decision will essentially depend on this network, if it allows to obtain a meaningful representation. This on one hand, and then on the other hand, it will depend how well your attention mechanism find the important instances. This is a very simple attention mechanism, but you can use other attention mechanisms. For example, you can use transformers, graph neural networks, and all that will influence the diagnosis. Yeah.
Okay, there are two more questions here in the Q&A.
Okay.
One from Abbar Shafiq. I would like to know if the fatty tissue are in majority in the bud. Does that influence the inference? Because fatty tissue is mostly white background.
Yeah. I get okay. I think fatty. You mean the white the white background here is removed in this patching process, so it doesn't influence the prediction. Oh no, I mean, I think you're okay. Okay, no, I don't know. I think now okay. The good thing about this one is that this fatty tissue won't be removed by the segment. Okay, I know now. I know what you mean. The fatty tissue won't be removed by the tissue segmentation tool if the segmentation is properly done. Okay, so I think I answered that.
Okay, there is another question from Ricky Walsh that say, I've heard that easy or obviously abnormal patches can highly influence MIL. Have you observed this to be the case? Or are current methods also capable of segmenting less obvious areas too?
Easy or abnormal patches can highly influence MIL. Have you observed it to be the case? Okay. In my experience, yeah, what you will observe in practice is that, let me go through this, is that abnormal, like as you term them, highly abnormal patches will take almost all the attention. But if you have a meaningful representation of the patches in a meaningful and a good multiple instance learning model, it will be able to localize, it will still be able to localize somehow less easy areas or patches. So it will still work, but it will depend on the application.
Okay, maybe there are two more questions, and this could be, we can answer these two questions and then pass to the notebook to
Okay.
need to last very, very much. And then if there are more questions about the meal or more, let's say, theoretical part or not that hands-on session, we can answer in the end at the end of the session. So
okay.
Here Jasmina say, does the use of overlapping and non-overlapping patches affect meal performance?
Yeah. In my experience, I say this a lot, but if you use a good feature extractor here, a good neural network here, you will, if the mechanism you use to extract features from your patches is good enough, you won't need to use overlapping patches. And in my experience, is better not to use non-overlapping patches, because essentially, if you use non-overlapping patches, you just extract less patches, your bags are smaller, and training is easier.
Okay, and then the last questions here, how to approach multi-class classification with MIL, where we have only few slides, like around 100 in total, and some groups have only around 20 slides.
Yeah, I think like this is the major problem when you are working with medical data. It's like you don't have labeled data. Even if you use multiple instance learning, you will end up, as you said, having 20 slides. So you need to first extract very good representations using foundational models, etc., etc. And then I don't know, somehow use techniques like weighting the loss function, maybe repeating samples, maybe introducing synthetic samples, doing some kind of data augmentation. You need to resort to classical tools in maybe computer vision or like in machine learning in general.
Okay, nice. So then if there are more questions about pathology, multiple instance learning, or the library, can be answered at the end of the session. Now we can go with the hands-on part, the practical part.
Yeah.
So you are going to share a Jupyter notebook, right? That it's going to
Let
be
me find it.
publicly available soon. So
yeah, let me find it. Okay.
Yeah. Also, if anyone has questions during this practical part, just
them in the
pop the
chat.
question in the Q&A, and I think that Francisco can interactively answer that questions. Okay. Maybe you can put it a little bit larger, the font size, because you have a very large screen, right?
Yeah, I think you can see this.
I think it's better. Yeah. If someone has issues, maybe you can put it in the chat and we can see.
And you see
Thank
this
you,
like this?
Francisco. Yeah, I think this could be
Yeah,
really good.
now it's good. Yeah.
Okay. So this is like, as Miguel said, the practical part. For this, you have an introduction to the topic here in the first cell of the notebook. The idea of this practical part of the tutorial is to be able to detect. I'm gonna remove all my, because I cannot see. Okay. The goal of the, as I said, the goal of this practical part is to develop or to train a multiple instance learning model to detect breast cancer metastases from whole slide images. We're going to be using the Chameleon 16 dataset, and maybe a lot of people here know this dataset. This is used in almost every paper on multiple instance learning. The good thing about this dataset is that we have the labels of the patches, so we can use them for evaluation purposes. And yes, as I say here, we will prepare the data using Trident, and then we will train a simple tension model. Okay. So you will have a GitHub repository. I maybe can open this, but I didn't want to. Maybe I can open this here. You will have a GitHub repository because you will need some other files that I have given to you. And well, this will be in the GitHub repository. You can just download them. And you will also need to, as I see here, you will need to download the original Chameleon 16 dataset. I cannot provide the dataset for you because it's so big, it's very big, because the original Chameleon dataset has the original whole slide images files. So, but you can download it from here, okay? As I said, the idea is to use torchmil. I'm going to open it. It's our library. And the idea is to show you how easy you can train a model using this library, okay? Okay. You will need some basic setup. You will need an environment to run Trident. Then you will need an environment to run torchmil. I prefer to create two separate environments so that there are no conflicts. but the environment part is up to you. This is just a recommendation. Okay, so you will need to define a path, two different paths. The first one will be the treatment directory, the directory where I want to open the questions because the treatment directory is where treatment will save the patches, the processed data. Then you will have the TIFF directory, is where the original Chameleon 16 has been downloaded. Okay. Okay. So the first part in the notebook is to actually pre-process the data. As I said, we are going to be using Trident for this. First, because it's a really good tool, and second, because torchmil is prepared to work with it. Okay. So yeah, there are some explanations. Every explanation I have put here is already is what I've said in the presentation, but I wanted the notebook to be self-contained too. So yeah, here we have as I explained, we need to segment state and then to patchify the images. And for this, we're going to use Trident. The good thing about Trident is that only with one command, you will obtain the patches of the whole slide image. I need to refresh this. You won't obtain the patches. You won't obtain the coordinates of the patches. And with the coordinates, you can extract the patches, okay? So if you run this command, you will specify where your whole slide images are, where you want to save them, which patch encoder you're going to use. This is actually very important. I'm going to talk about this in a few minutes or seconds. The magnification level and the patch size, okay? Whole slide images are usually taken at different magnification levels, so you need to specify at which level you want to obtain the patches, and then the patch size at that magnification level, okay? So, as you can see here, we are using the conch model, which is this is a model that has been trained using self-supervised learning on a lot of patches, on a huge data set of patches. It's very important. Sorry, what will Trident do is first segmentate the tissue, extract the coordinates, and then it will extract its patch corresponding to its coordinate, and then it will transform its patch into a feature vector using this model, okay? You can omit this patch encoding part in case you want to use your own patch encoder, or you want to, I don't know, you can even, maybe you can even use PCA to extract features. Anything is okay in this step, but it will largely influence the performance of the model we will obtain, okay? So once you have run this command, you will obtain this dataset structure, okay? You will obtain H5 files that are the features that Trident has extracted for us and the coordinates of the patches, okay? Okay, at this point, you can already train a multiple instance learning model, but we're going to do something else so that we can evaluate the performance of the model at the patch level. Let me look at the chat because, okay, in case there is any question. Okay, as I said, the next step is going to be extracting the patch labels. As I said, this is not necessary. You won't be able to extract them in a real scenario, but it's really useful for evaluation purposes. We want to obtain something like what we are seeing in this figure. We want to assign a number, a label to each patch, okay? How we do it? I have given to you in the repository a script, which is called extract labels chameleon16.py. The idea of this script is to go patch by patch and look at the proportion of cancerous tissue inside that patch. if the proportion of cancerous tissue is above or is greater than some threshold that has been predefined, you have to specify that, for example, 0.5. Then we're going to assign a label of 1 that will tell us that the patch is positive. Okay, I think, okay, this number should be 1024. Okay, sorry. Okay, so what you are specifying here is a CSV with the label of the whole slide images, like these are the bag labels. Then you will specify a mask directory. These masks essentially tells you are annotations at the tissue level, at the fine-grained annotations. Then you specify the coordinates that has been extracted using Trident, and a directory where you want to save the patch labels. Okay, and then you will have an HV file for each whole slide image, and that file will contain the patches, the labels of the patches. Okay. Okay, so the next step. So now imagine that you are at this point. You have already executed the 2 commands I have just talked to you about. So we can actually take a look at the patches. Okay, we can take a look at 5 of the patches we have extracted from a whole slide image. These are, as you can see here, you have a patch, you have the coordinate of the patch, and you have the label of the patch. Okay. You can see there are different kind of tissue, different structures, cells, etc. Okay. The next thing we can do is visualize the whole slide image. And for this, we use this function that essentially reads all the patches using its coordinates. And we can visualize a representation of the whole slide image using a function that is called patches to canvas. Oh, sorry. This function is in torchmil, and there is a module dedicated for visualizing whole slide images. And this function, essentially what allows you to do is you will give it the patches that you have extracted. These are a list of images and the coordinates and a size, and the size you want to precise each patch into, okay? And you will obtain this thing here, this whole slide image. This is a low dimensional, let's say, representation or low quality representation of the whole slide image. We are representing a gigapixel size image in a very small image here. This is only for evaluation purposes. And then you have this draw heat map, but essentially you will give the canvas, the whole slide image you have plotted, and then you will give it the patch label, okay? Also, you will give it the coordinates, and it will place a color depending on the labels of the patch. You can personalize that. It's in the definition of the function. You can personalize that. Okay, here you can. So okay, this is like somehow introduction, like data preparation. The next step, we're going to use PyTorch, or so the next step will be to define a data set. In torchmil, there is a huge list of data sets. For example, you have here a lot of data sets. And one of these data sets is called Trident whole slide image data set. The idea of this data set is that you can use it for the files you have extracted using Trident. Okay. And it's very easy to instantiate this data set. You just needed to give it the Trident directory. Where are the labels? Like these are the bag labels. This will be a CSV file. You have to specify which feature extractor you're using. In our case, we are using conch. And I see a question. I will finish explaining this, and then I will answer the question. And you can also specify the patch labels in case you have them. And there is a very important thing here, which is the bag keys. Okay, the bag keys essentially you are essentially telling the dataset which things of the dataset you want to load. The X is the feature matrix, Y, the uppercase Y is the bag label, the lowercase y is the patch labels, and then you have the coordinate and something that we call adjacency matrix. This is used essentially by some models that are based on graphs. This adjacency matrix tells you which patches are connected between them, okay? Which patch is connected to which patch, okay? And we can print one item in the dataset, and as you will see, it will give you a tensor tick. This is an object. It was developed for another library for reinforcement learning, which is called torchmil. And it's used inside PyTorch. It's pretty much standardized. So you can use it to create patches, and every operation that you can do in PyTorch with classic tensors has been adapted to TensorTick. That's why we use them. So essentially you have different keys and it will return you an object. These objects are what we specified before in the back keys parameter. Okay, I see two questions and I think someone raised their hand. So let me first answer the question. It says, how do you assign patchwise label? Do you use a slide label? Let's say we have mile with 58 slides, which can we have numerous patches? Do we then extract the patches and just assign 0, assuming this is our label? Okay. How to assign the patch label? This is done in this script. The idea is that you have, okay. The idea is, imagine you are given, for each whole slide image, imagine you are given a whole slide image, and what you know about that whole slide image is the bag label, okay? This is given by this CSV path. If the bag label is 0, okay, you automatically know that all patch labels are 0. Why? Because if the whole slide image is healthy, all the patches are healthy. Okay. If the patch label is, if the bag label is 1, is positive, then you take a look at each patch, and you have the annotation for each pixel. This is what is really good about Chameleon, is that you have annotation at the pixel level. Essentially, you have for each pixel, you have an annotation that tells you whether in that pixel there is cancerous tissue or not. Okay. And using that information, you can compute the amount or the proportion of tumor pixels in the patch. Okay, this is explained here. And if that proportion is greater than some threshold, you essentially label the patch with the positive label with 1. Okay. Okay. I think I can. Okay. There is another question. So from your experience, given a foundational embedded network, how many whole slide images are required to get a decent performance using multiple instance learning? Let me discuss this later. And because I want to highlight again the importance of the foundational network. Okay, so let me answer this later. Okay. There was a hand that was raised. I don't know if I can see it somehow. I don't know. I cannot see it now. So, okay, I will continue. If it was by accident. Okay. 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 So we have already created our data set. And the next step is to do mini batch or do batches of bags. As you can see here, we're going to be using batch size equal to 1 in this notebook. But if you want to train with large scale data, you will want to use batches of data. The thing about multiple instance learning in general is that each bag has different size. This is something that may also happen in other fields like sound and like text, where the different instantiations of our data have different sizes. Okay, as you can imagine, each whole slide image will have a different number of patches. So to be able to do batching, you need to solve this somehow. The way we have chosen to solve it in torchmil is to use a padding approach. Essentially, what we do is we fill all the bags in a batch with a padding value, which you can personalize, so that they all match the bag with the largest size. Okay. Once you do that, there is a collate function in torchmil to do that. This process is called collation. When you have collate all the things in your bag, you need to collate your feature matrix, your adjacency matrix, your coordinates. In some models, in practice, you will want to know which instances have been paired at. Okay, when we do collation, what we are doing essentially is adding fictitious instances. These are instances that are not real. So we want to, inside the model, when we do computation, we want to remove these fictitious instances, okay? Or these fake instances. And for that, we use a mask. A mask tells us which instances are fictitious and which are not, okay? This is not going to be important in this tutorial because we're going to be using a batches of one, but it may be important if you want to use a larger batch size. Okay, so now we have our data loaders, and the next step is to actually train the model. Which model are we going to use? I've explained AVMIL is really simple, so I'm going to use this model. But the thing is, I'm going to implement it from scratch in this tutorial. Why? Because it's really easy. It's just a couple of lines. This model is available in torchmil, as there are many other models. You can go here, you can go a model, the models directory, and then you have a fair amount of models you can try. But creating this, why I'm creating this from scratch? Because because it allows me to explain how to create models in PyTorch. As I said, we extract features from each patch. Okay, this line here, what it tries to explain is how to transform an patch image into a feature vector. Okay. This model that I'm using here is a conch model. As someone has pointed out, is a foundational model. It means that it has been trained using a huge amount of patches using self-supervised learning. And these models don't need labels to be trained. These models extract meaningful representation of patches, and is, in my experience, using a foundational model is very important to obtain a good performance. And as you will see now, using a foundational model will allow us to obtain a very good results in this data set using this simple AVP model. Okay, because why is that? Because this representation already carries a lot of information for each patch. Essentially, the discriminative information, the information that allows us to separate positive instances from negatives, is given by the foundational model. And the multiple instance learning framework just extracts it. Okay. So this is, I put here the equation of AVP model and how to define a model in torchmil. You can define it just a torch module, and these are all the layers that will be in the model. And one important thing is this criterion. This criterion is what the models is going to use to train. Okay. In this case, we're going to be using a binary cross entropy error loss, and the model definition is straightforward from the equations. We are given our X, which are the features of the model, and we transform the bag or the features into one-dimensional value, one-dimensional vector. This will be the attention value. We remove the attention values corresponding to those fictitious instances, and then we apply the softmax, and then we compute the aggregation, and then we fed this back representation into a classifier. Okay, and there is another parameter here which returns the attention dx, which we'll use to visualize the prediction. And then it's very important that when you are creating a model, you define this compute loss function. Why? Because as we will see later, we have a trainer object that essentially will call this function to compute the loss of the model. Okay. This compute loss receives the back labels and everything that the model needs to do the forward pass. Okay. If your model uses an adjacency matrix, you can put it here. If your model uses the coordinates, you can put it here. There are different models in torchmil that use this information. Okay, you can see examples in the web page. Yeah. So as I said, we're going to be using this trainer class. Essentially, this trainer streamlines this trainer collects the training procedure that you need to perform when you want to train a model in PyTorch. Okay, but is personalized for multiple instance learning. Okay, so you define the model, you define your optimizer, you define your device, and you can define the metrics you want to see during the training. Okay, you can also define an objective metric. Will tell you in case you want to do, for example, early stopping. Okay, and then you can train the model. The good thing about torchmil is that imagine that for some reason you want to use your own trainer. You can define your own trainer, but also you can use external tools to train a model. For example, you can use PyTorch Lightning. There was another. You can even use the accelerate library from Hugging Face. Is open is designed to work with all those tools, okay, which are really useful. Yeah. Okay, so as you can see, we have run only 5 epochs, and at the end, we already obtained really nice results, very good validation results. And so yeah, let's evaluate the model. This evaluation is just to show you the test result. We're going to evaluate the model in the test data set. You can see we obtain really good results. As I said, you can repeat this process using different features. For example, if you use, so for example, features extracted with a ResNet model pre-trained on ImageNet, the results will be worse. Okay, so it's very important to use a foundational model to extract features. Okay, and what this is the last part, and this is what I find most interesting about this, about multiple instance learning, because essentially it allows you to discover things you didn't have at training time. Okay, so you can choose a whole slide image, you build the back, and you obtain the keys of the back. Okay, you obtain the feature matrix, the label of the patches, and you do a forward pass through the model. And you can use the draw heat map or slide image function from torchmil to plot the attention values. Okay, this is what I show you. Observe that we have only trained for 5 epochs, and the model is already able to discover where is the cancerous tissue, and we didn't give any information about this in the training loop. We only gave the model a back label, and it's still able to recover where the tumorous tissue is. I find this really exciting or really interesting because imagine you want to somehow discover new.
Sorry,
Oh.
Francisco.
Yeah.
The session is scheduled to end in an
Yeah.
hour, so if
Uh,
you can, yeah,
okay,
Diana is
I
saying
will.
that another session is going to start in 15 minutes. So if you
Okay,
can,
yeah. I will. I just need 5 more minutes. Yeah.
okay.
Yeah, 5 minutes I will be finishing. So what I said is that imagine you want to get new biomarkers for a cancer, new type of cancer, and you have whole slide images labeled. You can essentially train a multiple instance learning model and take a look at the attention value, where the model is giving important, where the model is placing the attention. And maybe you can study those areas to find an important tissue structure or something that can be important to treat that disease. So yeah, that's all. Yeah, I think there are no questions. Please drop the Jupyter notebook. Okay, so yeah, this is everything. I will make the GitHub repository is not public. It's not public, but I will make it public available soon, like after the talk. So this is all. Yeah.
Yes, this session is recorded, and also the Jupyter Notebook will be publicly available. Also, there are more tutorials of torchmil in the web page of torchmil, right?
Yeah.
So also, if you have further questions, feel free to reach out Francisco. He will be very kind to reply of your question.
Yeah.
Thank you very much for being here, Francisco, and thank you to Diana and Rachid to organize everything.
Yeah, thank you.
And to all the people that attended.
Yeah, thank you, everyone. I hope it was interesting for you.
Thank you.